once we cover the concept of light today in the mathematics of the next class period, we've covered everything that we need to know when it comes time for this test. Okay, to begin with, when I flicked on the light switch this morning, light magically appeared in this room. It's not magic. It's science, ladies and gentlemen. Inside these gas tubes of light bulbs hanging above our head are atoms. After all, gas is a form of matter, which means you have stuff. You have atoms that compose it. A few different gases in here. I know mercury is one of the gases that are in these bulbs, which is why we're not just supposed to break them open. Mercury is not a good gas to breathe in. How the creation of light works is, first off, electrons absorb energy. When I flick on that light switch when I came in this morning, electric energy pulses through those bulbs. This could be heat energy. Think about when you burn stuff. Why fire good? Fire give light. Well, heat is a form of energy. That allows it to happen. Why does our sun give off energy? There's a lot of heat created in that fusion reaction for the sun that's exciting electrons. When electrons get excited, they move to a higher energy level. We call that an excited state. So for example, up on the whiteboard, I have a picture of board diagrams of things. Any of these dots, any of these electrons on here can absorb energy. And one of the things we're going to talk about today is how different electrons absorb different amounts of energy. And with that, different amounts of light can be given off, or different colors of light can be given off. So imagine any of these electrons all of a sudden jumping up. Heck, the valence electrons could jump to a higher shell. I mean, even though I didn't draw other shells because there's nothing in it, they could jump to an even higher shell as well. So step number one in the creation of light, there has to be energy involved. Energy is put into an atom. The electrons respond by jumping up in the air, not really the air, to a higher energy level. However, when they are at that excited state, they cannot stay up there forever. So what happens is they will eventually fall back down to what's called a ground state. When they fall back down to that ground state where they normally are, that energy that they first took in is now released. It's released in the form of light. What I'd like to do then is I'm going to switch over to Smart Notebook and I'm going to do a board diagram example of this to show you a little bit more. And you're going to see this on the packet that you're working on later today as well. So I just want to get you used to using the board diagram for this. Again, remember, the board diagram is not an accurate representation of the atom, but it is useful for a fair amount of things. I tried to use it to explain ionization energy and electronegativity and atomic radius when I gave back your labs. We also typically use it to describe light and how light is created. So I'm going to draw a generic Bohr model for this right now. So I don't care what element it is, really. Here's your nucleus. Okay. We want to call it something, let's call it magnesium. It's got 12 protons in it. But since I'm not giving you a mass, I could care less about the neutrons. Magnesium has 2 electrons in its first shell. Remember, it's 1s2. It has 8 electrons in its second shell because it's 2s2, 2p6. And it has 2 electrons in its third shell. Now, let's start with, how about this outer electron? That electron is kind of far away from the positive center, which means there's not a lot of attraction there. Remember what we talked about a little while ago? That means if it were to gain energy, it can jump pretty easily, and it can jump up to another shell. Now, I didn't draw another shell, but there's other shells there. There's other energy levels. So maybe it just jumps up one energy level. But just like a kid that's all hopped up on sugar and they get really excited and they're, at a higher energy state, I would say, eventually you come crashing back down. And that's what happens when light is created, is they fall back down. And during that fall, light is given off. Different elements can require different amounts of energy. For example, how about this electron right here? Maybe since it's close to the nucleus, it has to absorb more energy to get away. So maybe it jumps up 2 rings, and then it falls back down. It can give off light at that point. Maybe this one can jump up 3 rings, fall back down, give off light. So the size of the jump and fall plays a role in what type of light is given off. And I'm going to go over that a little bit more on the next couple of slides. But to start with, we like to use the Bohr diagram to demonstrate how light is created. An electron gains energy. Again, when I flicked on that light switch this morning, electricity, electrical energy went into the gas atoms in these gas bulbs, these light bulbs above us. That electricity allowed electrons to jump up and then fall back down because you can't stay excited forever. During that fall back down, that energy that was originally taken in is now given off. We use light to not only go over how electrons behave, because again, electron behavior is part of the atom unit, but also to introduce you to the second law that we will go over now in chemistry class. Last unit, we spent a lot of time with the conservation of mass law. The idea of the amount of mass to start with equals the amount of mass to end with. You can't gain or lose matter. Energy works the same way. So the first law of thermodynamics is the conservation energy law that says the same amount of energy that is absorbed by the electrons is given back when they fall back down. So what we're going to go over is there are some higher forms of energy and some lower forms of energy. You have a picture of a fire. Fire gives off light because you are heating, adding energy to molecules. Those electrons then gain energy, they jump up, they fall back down. That's what's giving off light. Now, one of the labs that you are really going to like this year, you are doing next week. You are going to be burning different stuff. And depending upon what you burn, it's going to show different colors. Because different elements absorb different amounts of energies to cause their jump and their fall. And really that's what I need to get into now is these first couple of slides we're just talking about how is light created. Electrons gain energy, they jump up, they fall back down. But now we need to go over that there's different types of light. All the different types of light fit into what's called the electromagnetic spectrum. Heck, I have a poster of it back by the safety shower where it says electromagnetic spectrum. All the different forms of light out there fit into that broad category. Light is measured in wavelengths. And we're going to talk about that wave property of light more today and next class period. Some waves of light are really long. Think about it. 10 to the 5th meters, if you remember your scientific notation, would be the same as a 1 with 5 zeros after that. That's 100,000 meters or 100 kilometers. So one wave of light can be 100 kilometers long. That's really, really long. Some waves of light are really, really short. 10 to the negative 13th is ridiculously small. Based upon the length of the wave, we get different forms of light. For example, you are aware of the rainbow, Roy G. Biv, red, orange, yellow, green, blue, whatever indigo is, and violet. Visible light, the light that we can see, is a very tiny amount of that visible spectrum, 400 to 700 nanometers. NM, nanometers. This was a metric conversion we taught you last unit, because starting next class, we need to use that metric conversion for the math we're going to do. Again, in the back of the room here, I have a poster that has a graph that goes all the way across that shows different lengths of waves. Visible light is a tiny sliver of all the types of light that are given off. This is the only type of light that our eyes can pick up. Okay, compared to all the forms of light, visible light is a very small amount. It makes you think of how spectacular the human eye is that it can pick up that small. Or maybe we think it's not very good because it can only pick up a small amount of wavelengths that our eyes then can perceive as light. There are some forms of light that are higher energy. UV is ultraviolet. Remember, this is put on your sunscreen on a sunny day, or else the UV light will be bad for you. We're going to talk about why UV light is bad for you. Like, we're going to do some math to prove that UV light is bad for you. But ultraviolet radiation, some forms of light are high energy. X-rays. If you've ever received an X-ray before, that is high energy light that's passing through you. It's so high of light that the X-ray technician is never in the room with you. Because if they're exposed to that high of energy light on a consistent basis, they are going to have health issues. Gamma rays is even higher energy than that. When we talk about nuclear decay and radioactivity, so if you ever watch movies and there's radioactive material there and people are like, oh no, they're referring to gamma rays, even a higher form of energy. So we can't see these forms of light, but they do exist. There are also lower forms of energy. Now, maybe I should have wrote down IR is infrared. So I'll write that up here. Infrared. Now, there are infrared goggles. You can see kind of the heat signature of things given off. If you ever watched any of the Predator movies, you saw through infrared. Lily, have you seen Predator? No, you should. It's a lot of science in that. Just that's actually it. That's the only science in it is they can see infrared. We probably never thought of that thing in our kitchen as light, but microwaves is a form of light. Microwaves is a long, low energy wave. And what happens is the food molecules absorb that. And when they absorb energy, they start moving around a little bit more, and they move around a little bit more, and that creates heat. That's how your food gets heated by a microwave, is by absorbing those waves. Radio waves, even longer and lower energy still. I mean, these are the ones that could be about a mile long. How do we have some of our communication from device to cell tower or radio station to tower? It's based upon those types of waves. And those waves carry from one point to another, and then whatever device we're using is able to make sound come out the other end. Because sound also occurs in waves. So we need to be familiar with the different types of light. There's visible light, there's higher energy, your ultraviolet, your X-rays, your gamma rays, and there's lower energy, infrared, microwaves, and radio waves. Now, light is a moving wave, but there's more to it than that as well, so we are going to have to go over that a little bit. What I want to cover right now is the relationship between three factors of light: wavelength, frequency, and energy. Again, what I'm going to do is I'm going to draw this out on the Smart Notebook as an example, and hopefully you can see these relationships. I'm going to draw two different waves of light. A wavelength is the length of one wave. It's not a tricky definition. So you can measure that like from peak to peak, from trough to trough. You could just do one oscillation. That's a wavelength. Which one, the top or the bottom, has a longer wavelength? Top. Okay, simple enough. Frequency. I mean, if you tune in on a radio station like 101.5 WIBA-FM, that is a frequency on your radio. And actually, when we do the mathematics next time, you're going to see the same unit that we use for frequency. A lot of car radios have that unit written on it as well. Frequency is how often something happens. So how often does the waves occur? Which one, top or bottom, has a higher frequency? Bottom, right? It happens more often. There's more waves per space. So we have what's called an inverse relationship between wavelength and frequency. Longer waves occur less often. Shorter waves occur more often. The last thing I had on my slide was energy. Looking at these two, which one seems like it has more energy, the top or the bottom? The bottom. A higher frequency wave is going to have a higher energy associated with it as well. And again, mathematically, we'll prove that next time. Low energies waves are longer waves. So we do need students to be aware of that relationship between wavelength, frequency, and energy. If I go back to my slide here, and distance of one peak to another, how often the wave occurs. So those are kind of the terms, but it's very common that we will assess students on that relationship between them. And one of the things that I'm hoping we get to today is a wave drawing activity. Remember, we got the sheets of paper out on the lab benches. Your lab report that you're going to do next week is going to have wave drawing on it. And we want you to be aware of that relationship between long waves are low energy and they don't happen very often. That's your microwaves, your radio waves. Again, just because you have your radio on and there are radio waves passing by you, that's not going to harm you. However, if you had X-rays passing around you all the time, that would be harmful because they are higher energy. Probably next class we'll talk about why that higher energy wave is more dangerous. Now, just like when you guys were turning in this trends lab last time, I said now we're getting into chemistry. Now things are getting a little more difficult at times as well. Not everything is nice and neat in chemistry. And light is one of those examples because we know the behavior of light. It behaves as a wave. However, we also know of a particle of light, which is called a photon. So when I show the jump and then fall, during that fall, that energy is released, although we refer to sometimes that energy as a photon, a particle of light. That does not mean that the mass decreases, and that's where things get a little goofy. That wave-like properties and particle-like properties exist for light. But light, again, behaves like a particle, and it behaves like a wave. Now, we don't actually do much besides make you aware of the term photon. After all, photography and everything else dealing with light and sight is based upon photon. We certainly focus more on the wave property of light. However, if we are to be accurate in what we are teaching you, we do need to mention this dual behavior of light. And as you're wrapping up, I believe this is the last thing that I had. Why are we covering light? Because in our atom unit, we have to know about the parts of the atom, the nucleus and the electrons. And as hopefully you've seen over the past 3 weeks, the electrons play a major role in the behavior of an atom. And with that, why do we have light in any situation is due to electrons getting excited, jumping up, and falling down.